Hello guys, welcome to another chemistry class. My name is Mr. Yomide and today we are going to be looking at the periodic table. In this class we are going to be looking at the following. Why do we need to classify elements? What are the various attempts by scientists at classifying elements? What is the modern periodic table? What are the trends in the modern periodic table? Now, in the 19th century, chemists began to categorize elements based on their physical properties, that is what they could see, and their chemical properties, that is the behavior of these elements when they undergo chemical reaction. Now, after the evolution of this classification, we are able to get what we call our modern periodic table. In 1789, Lavoisier classified elements into metals like iron and aluminium, non-metals like sulfur and carbon, gases like oxygen and nitrogen, and earths like silicon. But this classification was not sufficient because it led to a lot of overlaps between various groups. For example, we could have non-metals as gases, we could have metals as earths, and this caused a lot of confusion. Dobereiner in 1829 decided to classify elements into groups of theories. Now, these groups of theories had similar chemical properties. They had what? Similar chemical properties. That is, they undergo the same or similar types of chemical reactions. For example, chlorine, bromine, and iodine undergo similar chemical reaction. Lithium, sodium, and potassium, they also undergo what? Similar chemical reactions. But this grouping system also had a lot of difficulties because it didn't capture the full picture. Now, Newland came in 1866 and decided that instead of classifying the elements in groups of theories, let us classify them what? In groups of 8. He noticed that when arranging the elements in order of increasing atomic mass, that certain properties repeated every 8 elements. Now, this was an improvement because he wasn't just arranging them based on physical and chemical properties, but he was arranging them based on what? Increasing atomic mass, which led to what? The exposure of a certain pattern, a certain rhythm. But this wasn't sufficient because every 8 elements, the repetition of properties every 8 elements could not capture the full scope of all the elements. It was only true for a certain region of the elements we now have. So we can see his classification system here, where he classified lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine. We could see that fluorine and chlorine are under the same group, which is group 7. Oxygen and sulfur are under the same group. Nitrogen and phosphorus are under the same group. But this is classification system was, as you can see, is grossly inefficient because we have boron and aluminium, which have different chemical properties being grouped together. So we needed to work more and do a lot of more research towards get a more efficient classification system. Newland, one thing to note about Newland was that he was the first person towards list elements in increasing order of atomic masses. Now, this point is very interesting because this point laid the foundation for the modern periodic table. It laid what? The foundation for the modern periodic table, because the idea to what? Arrange these elements in what? They are increasing number of atomic masses was a very brilliant idea, and it was the idea that subsequent scientists worked on to develop a more efficient periodic table. Now, Dr. Meyer in 1869 decided to use what the atomic volume curve for its classification. Now, this if you can see that this atomic volume curve is based on what a graph of the atomic volume against the atomic weight. Now, this was progress, but it didn't capture certain properties in the periodic table. You can see that the peaks of some of these of this curve, we have lithium here, we have sodium, potassium, rubidium, and cesium, are elements with what similar chemical properties, but the elements within them, you can see we have 1 2 3 4 5 6 7 8, which is similar to what the former classification system, which grouped in what 8. We have 1 2 3 4 5 6 7. You can see that there's a bit of instability there, and you can see 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16. You can see that there was no constant rhythm to its classification. It was a great idea, but it didn't capture it didn't capture the properties, the full properties of the elements in the periodic table. Now, in 1869, Dmitry Mendeleev published the first periodic table. Now, Dmitry Mendeleev is commonly known as the father of what the periodic table, because he was the first person to publish the periodic table. Now, his periodic table was based on what the periodic law, Mendeleev's periodic law. Now, what's the periodic law? It says that the physical and chemical properties of elements are a periodic function of the atomic masses. Remember that Newland was the first person to what make use of the increasing order of atomic masses to classify elements. Now, Mendeleev improved on this to derive what the periodic law. This periodic law states that the physical and chemical properties of elements are a periodic function of their atomic masses. Now, this periodic law enabled Mendeleev to what develop the first periodic table, but this periodic table didn't have provision for the actinide and lanthanide series, so there needed to be what a bit of modification. Now, before the modification, when Mendeleev was preparing his periodic table, there was only 63 elements known. Now, Mendeleev's periodic table was able to predict some elements that were not discovered. Now, he grouped these elements. His periodic table had a structure of groups and periods. Now, the groups are what the vertical rows, or what we call columns, and the groups had 8 vertical rows. The 7 groups were subdivided in A and B. The 8th group had what 9 elements in the group of 9 each, and the periods had 7 horizontal rows. Now, that was the initial periodic table developed using what the periodic law. Now, what were the advantages of the periodic table that Mendeleev developed? I told us that it was able to predict some new elements that had not been discovered at that time, like germanium and selenium. Now, it led to a systematic study of elements and what the correction of some already mistaken atomic masses, like that of what beryllium. Now, do you know that when Mendeleev finally published his periodic table in 1905, no one knew the structure of an atom? Isn't that interesting? Classifying something without even understanding the structure, that shows the significance of Mendeleev's discovery at that point. Now, this led to what? An element being named after him. Now, if you check your periodic table, you check the element with atomic number 101. It is called what? Mendelevium, which is named what? After what? Mendeleev. A few years after, in 1913, Henry Moseley, through his work with X-rays, determined the actual atomic number or nuclear charge of the elements. Now, he then rearranged the elements using what? In the order of what? Increasing atomic number. Now, although his research was altered during the World War, when he was killed by a sniper at the age of 28. That's a pity. That he could have probably discovered some new amazing things, but his short life was enough to give us a modern periodic table. Now, after plotting a graph, he was able to show that the atomic number is a more fundamental property than the atomic mass. Show that the atomic number better described an element than its atomic mass. No wonder. Making use of atomic masses to classify elements would have resulted in mistakes classifying isotopes as different elements. Making use of atomic mass to classify elements would have resulted in mistakenly classifying isotopes as different elements. But with the atomic number, we can be saved from that mistake. So this is Moseley's plot of the frequency and the atomic number in 1914. Now, with the knowledge of Moseley, the periodic table was then modified. That is, Mendeleev's periodic table was then modified to what we currently call the modern periodic table. Now, the modern periodic law states that the physical and chemical properties of elements are a periodic function of the atomic numbers. You can see that the only thing that was changed there was mass and number. Instead of mass from Mendeleev, numbers was used because the atomic number describes elements better. So the physical and chemical properties of elements are a periodic function of their atomic numbers. Now we can see our modern periodic table. Looking at the modern periodic table, we can see that we have groups, periods. Now, like I said, the groups are the vertical columns, while the periods are the horizontal rows. Now, come to the keys here. You can see this color, the lilac or purple color or light purple color represents the S block of our electronic configuration. That means every part of the periodic table with this color, a lilac or purple color, is have their electric configuration for the S block, and we can see that is group 1 and group 2 elements. Group 1 and group 2 elements. So we call this part the S block. Now, the next is the p block, which is color blue. That is from group 3 to group 0. Group 3, group 4, group 5, group 6, group 7, and group 0. Now, in some textbooks, the group 0 might be replaced with group 8. So don't be confused. Group 0. Now, why is it named that? Why is it given that name? Because it has a perfect octet. That means there is allowance for 0 extra electrons. It has maximized the available pockets for electron on its outermost shell. For example, helium has 2 electrons in its outermost shell, which is the maximum possible. Neon has 8, which is the maximum possible. That's why it's called what? Group 0. 0 space for what? Extra electrons. Now we are so this block from group 3 to group 0 is called what? The p block. Now we have what? The d block, and the d block is made up of what we call transition elements, which is in the middle of the periodic table. You can see it with the you can see it with the yellow color, yellowish coloration, yellowish orangish coloration. Then we can see the F block with what? The pinkish coloration, which contains the lanthanide and the actinide series. So this transition element is called what? The D block. That means the electronic configuration is for the D block. Now, for the F block, we have the lanthanide and the actinide series. Now, this is another sample of the modern periodic table. Now, the keys here are different from the previous one, and I want us to also look at it. We can see this one is grouped into metals, metalloids, non-metals, and noble gases. Now, our non-metals are in blue. Hydrogen is obviously a non-metal. Now, when you can see, hydrogen is a non-metal, but it is placed in a group filled with metals. Now, that is one of the deficiencies of the modern periodic table. So, but scientists have come to accept it, that pending the time you can get probably a more efficient classification system, we just place hydrogen here because it has one valence electron. All the elements in group 1 have one valence electron, only one electron in the outermost shell. All of them in group 2 have 2 valence electrons. Everything in group 3, 3 valence electrons. In group 4, 4 valence electrons. Till group 7. For group 8, they have what? A stable octet, like I mentioned earlier. Now, the non-metals are in blue. We have hydrogen, then we have carbon, nitrogen, oxygen, fluorine, and others. Those are the non-metals. Then we have the noble gases. We call them noble gases. They are a special breed. Group 8 are the noble gases, or group, you can see it, group 8 here, or group 0. They are the noble gases. Then we have the metalloids. Now these metalloids behave both like metals and non-metal. They have characteristics of both metals and non-metals, and they form a zigzag border between what? The transition metals, or the transition metals, and what? The non-metals. So then we have the lanthanide series and the actinide series, which are also called rare earth elements. Now, what are metals? And what are their properties? Now, what are the properties of metals? We know that they are good conductors of heat and electricity. We know that they are shiny, they are ductile, can be stretched into thin wires, they are malleable, and they corrode when they react with water. So you can see some of the things we use metals for. We can use them in making machineries, cranes, metallic hollow pipes, rail tracks, nails, etc. Now, metals are usually solid at room temperature, except one. And the exception to this is mercury, which is what? Liquid at room temperature. Now look at this periodic table where we have shaded the areas occupied by metals in what? Wine color. You can see, apart from hydrogen, which is here, every other element in the group 1 and group 2, or group 1A and group 2, are metals. The elements in the middle and some of these elements here are also metals. Then the lactanide and actinide series are also metals. Now, these metals have subdivision. We have the alkali metals. Now, group 1 elements are generally known as alkali metals. So apart from hydrogen, the other elements in group 1 are called alkali metal, and they have what? One valence electron. We have what? Lithium and the others here. They are what? Alkali metals. And these metals are very reactive with water. Very reactive with water. Then we have what? Alkali earth metals. We have what? Alkali earth metals. Now, these have what? Two valence electrons. They are what? Two valence electrons, and they are in group 2. So you can see one valence electron group 1, two valence electrons group 2. Now, these alkali earth metals are also reactive, but what? Less reactive than what? Alkali metals. And why? Because they have two valence electrons. Now, in chemistry, when a reaction is going to take place, if you have one valence electron, you can easily give it out. But if you have two, it becomes more difficult for you to give it out. So that's why it is less reactive. Then we have what? Our transition metals in what? Color yellow. So when you hear the word transition, it simply means transition from what? Metals to non-metals. Now, these are less reactive than alkaline earth metals, and we have some special transition metals called what? The lanthanide and the actinide series. Can you see? We have the lanthanide series, which are shining and found in nature. We have the actinide series, which are radioactive and mostly man-made. So the lanthanide series are mostly found in nature. Remember the word mostly. Why the actinide series are what? Mostly man-made, and when they are even found in nature, they are not usually stable. They break down to form something else. Now let's go to the properties of non-metals. Now, non-metals are poor conductors of heat and electricity. They are not ductile and they are not malleable. They cannot be drawn into wires. They cannot be beaten into sheets. They are brittle and break easily. They are not shiny. They are dull. And we have a lot of gases that are non-metals. Now you can see this piece of sulfur here, a non-metal. You can see fluorine, sulfur. These are all non-metals here. Now, the areas in wine here are the areas in the periodic table occupied by the non-metals. We have our hydrogen here, and we can see our one element in group 4, 2 in group 5. Can you see? Just a step, like you are taking a staircase. 1, 2, 3, 4, and all. Those are the areas for what? Non-metals. Now, non-metals also have their divisions. We have our group 7, which we call halogens. Now, these halogens are very reactive. In fact, they contain some of the most reactive non-metals. Now, you can see the star, the ambassador for the group 7 is the fluorine, which also happens to be what we call the most electronegative element in the periodic table. Very, very reactive elements. Now we have what our we have our group 8 elements. We have our group 8 elements. We have our what group 8 elements called what the noble gases. Now they have 8 valence electrons except what with except helium. Helium has 2 valence electrons. Except what helium, which has what 2 valence electrons. But they've all occupied, like I said earlier, their maximum capacity for the outermost shell. Now you can see 1, 2, 3, 4, 5, 6, 7, 8. This shell can only take 8. 1, 2 can only take 2. Now these elements are happy because their outermost shell is filled and they don't really react. So they call them inert gases because they don't really react. And they are all gases. Now we have metalloids. Now these metalloids are very special, especially in today's industrialized economy, because a lot of semiconductors used in our circuits are what metalloids. Now these metalloids have properties of metals and non-metals. They are solids, they can be shining, they can be dull, they can be ductile, they can be malleable. Can you see they are sharing properties of what both metals and non-metals, but primarily they are what semiconductors. Now another example of a non-metalloid, apart from silicon that we had there, we have arsenic, germanium, etc. You can see the metalloids occupy a stair. You can see a stair is like just like you're playing Tetris. A stairway between the metals and the non-metals. 1, 2, 2, 2, 1, 1. So they form the boundary between what the metals and the what non-metals. That's why they share the properties. Now we have the periodic trends. What's a trend? In today's world, everybody uses either an Android or an iPhone. Now that's a trend. A trend is a pattern that is similar across a population. Now in chemistry we also have trends. Now in our periodic table we notice that some across the period or down the group there appears to be a kind of pattern in the properties of these elements. There appears to be what? A pattern, and that's the periodic trends we are talking about today. Now there are several important atomic characteristics that shows predictable trends that we should know. Now one of these trends is the atomic radius. Now what is the radius? Half of the diameter of a circle, right? Now what is the atomic radius? That's the distance between the nucleus and the edge of the electron cloud. What? The distance between what? The nucleus and the what? Edge of the electron cloud. Now we can see it is usually measured in angstroms. An angstrom is equal to what? 1 times 10 raised to a minus 10 meters. It can also be measured in what? Picometers. Now the atomic radius of elements get the atomic radius from elements in a group, or what we call the vertical column, goes from the smallest at the top of the periodic table to the biggest at the bottom of the periodic table. Now this is obvious because down each of the group an extra shell is added And once an extra shell is added, what happens? The atomic radius becomes bigger. Now we can see that with each step down the family, we add an entirely new energy level to the electron cloud, making the atoms larger with each step. Now, what of across a period? Across a period, because we add both a proton and a neutron, it increases the force of attraction between what the nucleus and the outermost shell, making the atomic radius shrink. So the increased attraction pulls the cloud in, making atoms smaller as we move from left to right across a period. Now this pull is caused by what we call the effective nuclear charge. So remember, down the group the atomic radius becomes bigger, but across the period it becomes smaller due to what the effective nuclear charge. That is what the pull of an electron from the nucleus. The closer an electron is to the nucleus, the more the pull it feels. So those elements with just one shell, the pull is stronger. But when we add extra shells, we have what they call the shielding effect. That means because the extra shells are farther from the nucleus, what happens? The pull is not as much. Now, when we have more electrons around the shell, it increases the pull as long as we have an extra proton. As in, when we add a proton and an electron, the pull becomes stronger. When we add what? A proton and an electron. But if we just add an electron, although the pull now the atomic radius increases downwards because as we go down, an extra shell is added. Hydrogen has one shell, lithium has two shells. As we go downwards, this one has 3 shells, 4 shells, 5 shells, 6 shells, 7 shells. So when there's an extra shell, obviously the size will increase. But across a period from hydrogen to helium, there's a reduction in size. From beryllium to boron, there's a reduction in size because as an extra proton and an extra neutron is added to the atom, it causes what? A pull that what? Shrinks what? The atom. So you can see this graph shows the direction of this arrow shows the direction of the increase in size. So downwards is an increase in size. Like this, in this direction, there's an increase in size. So you can see that it goes from the smallest around here to the biggest around here. Next is our ionization energy. Now, what is ionization energy? Now, the ionization energy is the energy that is required in the formation of ions. What's the formation of ions? It's the element required to what? Remove the valence electron. You can see the definition here. If an electron is given enough energy to overcome the effective nuclear charge, it can leave the atom completely. So an electron can leave the shell of the atom, and the outermost electron will be the one that has the highest tendency to leave. So the amount of energy to what activates that electron to leave the atom is what we also call the ionization energy. So when an electron is removed like that, the atom is no longer a neutral atom because the number of protons and electrons are no longer equal. Now this energy that is the ionization energy, is required is measured in what kilojoules. You can see the energy required to remove an electron from an atom is the ionization energy, and it is measured in kilojoules. The larger the atom is, the easier it is to what remove the valence electron. That means an atom with a bigger atomic radius will easily give out its electron compared to that with what a smaller atomic radius. So that's why you can see that the ionization energy and atomic radius are inversely proportional, because when the atomic radius is large, since it can easily give out the valence electron, ionization energy required is small. When the atomic radius is small, the force of attraction is so much that we require what a large ionization energy. That's why we say they are what inversely proportional. Now let us look at the trend here. Now ionization energy increases upwards in a group, unlike what the atomic radius. Now the ionization energy increases upwards, but what it reduces, the ionization energy increases upwards, unlike that of atomic radius. So we know that lithium, which is small, we have what a high ionization energy even when it has a very small atomic radius. You have what a high ionization energy because it has a small atomic radius. But the ionization energy also what increases across the period. Now look at this, is lithium, this is beryllium. An extra electron is added. When the extra electron is added, what happens? It becomes what? An extra electron and an extra proton is added, right? Remember? It becomes what's tighter. Like I said, there's more force of attraction, like I explained earlier. And since it becomes tighter, it becomes smaller. That means the ionization energy is going to increase. So when we are going across the period, the ionization energy is increasing, which will be represented by this arrow. It increases across the period and increases upward in a group. So we have it increasing from somewhere here towards the highest ionization energy being flowing here. Now, let us take this question. If an atom has a low ionization energy, will it be easy or hard to remove an electron? Think about the energy required to remove it. Is it high or low? Do you have to put a large amount of energy or a small amount? What if the atom has high ionization energy? Now, so let's answer those questions. If the element has a low ionization energy, that means you can easily remove the electron because the ionization energy required is low. It's just like having a 5-watt bulb and you have an 100-watt bulb. You might be able to power a 5-watt bulb with a few batteries, but for an 100-watt bulb you will need what? More batteries. So the same with ionization energy. When the ionization energy is low, it easily releases its electrons. But once it's high, you need to what? Supply more energy to the system for the system to what? Release an electron. Now, ionization energy can also be in levels. We can have the first ionization energy, which is to remove the first valence electron. The second ionization energy required to remove what? The second valence electron. The third ionization energy, and so on. Now, from the first to the second, there is what? A very large increase in ionization energy. So as we try to remove more electrons from the same shell, the amount of energy we need to supply increases largely. So next we have a metallic character or electropositivity. Now this is the measure of how easily an atom loses electron. Now you can see it's similar to ionization energy. Now we said an element that has a low ionization energy easily what loses its electron. So we can say that an element with what a low ionization energy is what highly electropositivity or has what a high metallic character. Now look at this. We can see that the metallic character increases down the group and reduces from the end of the group towards, so from the end of the period it increases down the group and also increases from the end of the period to the beginning of the period. It increases from the end of the period to what the beginning of the period. And you can see the metallic character goes like from this area which has fluorine here with the least metallic character or the least electropositivity to what to this part where we have what the highest metallic character or the what highest electropositivity. So the metallic character decreases, it increases down the group and what also what reduce and increases from the end of the period to the beginning of the period. Increases from the end of the period to the beginning of the period. You can see it here. So which element is most metallic? You can see it here. Find out. Now we go to what electronegativity and electron affinity. Now can you see that it's similar to what we just did? Now electronegativity is the directly opposite to what electropositivity. Now electronegativity, we said fluorine has the least electropositivity, but it has the highest electronegativity. We said elements that are highly electropositive, easily what gives out electrons, but elements that are highly electronegative easily what takes electron. They don't like to give. Highly negative elements don't like to give, they like to take. But highly positive elements what like to give, they don't like to take. Now we say that an element that likes to take electrons have what a high electron affinity. It likes to take electrons. It has what a high electron affinity. We say the electron affinity is the amount of energy released when an electron is added to a neutral atom. It measures the tendency for an element to accept electrons. Now high electronegativity elements always like to take electrons. You can see that an high electronegative element has what a high electron affinity. So electronegativity itself is a measure of an atom's attraction for another atom's electron. It wants to take what another atom's electron. So you can rate it from 0 to 4. And generally metals, like we said, an element that have a strong metallic character, we have what a low electronegativity. Non-metals that have a low metallic character have what high electronegativity, and we say they have what a high electron affinity. What about the noble gases? The noble gases, like I said earlier, they neither want to take or they neither want to give. They just want to be left alone. They don't want to take anything from you. They don't want to give you anything. They are satisfied. They are stingy and they don't beg. They are not collecting electrons, they are not giving it out. Now you can see the trend here. Electronegativity, you can see it's directly this graph is directly the opposite of the graph I just showed you earlier. Now you can see the electronegativity increases upwards and increases from the beginning to the end of a period. It increases upward the group and increases from the beginning to the end of the periodic table. So you can see that it from the least electronegative, which is what I told you to find out earlier, which has the highest electropositivity, and that's the least electronegative, and it has the least electron affinity to what? Yeah, which has the high electronegative and an element that has a very high electron affinity. Now for the, like I said, for the group 8 or group 0, they don't want anything. They want 0 electrons. They want to give out 0 electrons. They want to give out 0 electrons, and they want to take 0 electrons. They are not concerned with anybody. They want to just be left alone. What was the most electronegative atom? Wow, I said that earlier. Let's see if you remember. Fluorine. Why is it the most electronegative? Because it has a very small atomic radius, and which means it has, and I told us that when you have a small atomic radius, the nuclear charge will be much. Its outermost shell has 7 electrons. So 7 electrons with 7 protons, that means a very, very high electromagnetic attraction, which results in what? A very high nuclear charge. And remember, the screening effect is also negligible because it only has what? 2 shells. So the screening effect is what? Negligible. That makes it what? The most electronegative element. Now, reactivity. Now, this reactivity ties both electropositivity and electronegativity together. Now, elements that are at the extreme end of electropositivity and at the extreme end of electronegativity tends to be highly reactive. But elements that are in between, their reactivity what? Decreases. So now the best way to also understand this is to treat metals and non-metals separately, because metals react by what? Giving out electrons, while non-metals react by what? Gaining electrons. The most reactive metals are the largest, since they are what? The best electron givers, and I told us that they have what? The high electropositivity. Why the most reactive non-metals are the smallest, because they are the best electron takers and they have what? A high electronegativity. You can see those that are at the end, like I said, they are at the end. The one at this end, most electropositive, and the one at this other end, electronegative, most electronegative, and their reactivity in between varies. And like I said, for our group 8 or group 0, they are not concerned with reaction. They don't want to react. That's why we call them noble gases. Now we talk about the ionic radius. The what? Ionic radius. Now the ionic radius is often confused with the atomic radius. Now what's the difference? For the atomic radius, we have what? At each level we have what? Plus 1 proton and what? Plus one what? Electron. But for ionic radius, we only have what? Plus one electron. Which means going across the group in the periodic table, going down the group for both of them, there is an increase in radius. That means for ionic radius down the group, down the group so for down the group for both of them, there is an increase in what? Radius. So the ionic radius increases down the group, same with the atomic radius, because of this addition of shells. But going from the beginning of a period to the end of the period, for ionic radius it increases, but for atomic radius it reduces. Why? Because since there's an addition of proton and neutron and electron in atomic radius, it increases what? The what? Nuclear charge. It increases the nuclear charge because plus and minus, just like electricity, more attraction. But since you only have an electron without a corresponding increase in proton, the reverse is the case. This are just an extra electron, no corresponding increase in proton. So the size increases because there is no corresponding increase in nuclear charge. So that's why when you see elements with the same electronic configuration, but with extra electrons than a normal neutral atom, the ionic radius increases. That's it. Because ionic radius is radius of ions. It is when ions are formed we have ionic radius. Why atomic radius is for what? A stable atom, a neutral atom, an atom with no charge. Ionic radius is for an atom with a charge. So when these atoms, when the ion, when an element gains extra electron, ionic radius increases. But when it loses the electron, then it can what? Reduce. That's why I said it what? Increases down the group. So you can see cations, that means positive ions, are always smaller because they lose a whole complete shell. They are always smaller. But anions becomes larger because they gain extra electron without getting a proton. it becomes larger because the electrons are added to the outer shell without a proton to increase the charge. So you can see how a cation is formed. This is a valence electron, that is the outermost electron. Once this electron goes off, this whole shell is off. So this whole shell is off. You can see it, you can see the way it moved out. So this whole shell is off. So we are left with just this inner one. So you can see it when the cation is formed, the effective nuclear charge on the remaining one increases because you are now left with the inner one, and you have a lot of electrons. It shrinks. It shrinks because an electron is lost. That's why the cations are always smaller than the neutral atom. Look at it. You see the way it shrunk. It shrinks. It's going to shrink. But for the formation of anion, you can see an anion has a lot of electrons. Now it cannot lose all of these electrons. No, it's too much for him to lose. Instead, to form a stable octet, the easier way for him, since it already has 1, 2, 3, 4, 5, 6, 7, he just needs an extra one, make itself 8. So it's going to beg and collect one electron. And once it collects one electron, since the proton remains the same, it's going to lead to a bigger radius. You can see it. This is chlorine with 7 valence electrons. I've counted it. Once one electron is added to the outermost shell, you can see the nuclear charge is reduced because there is no proton added, and it what grows. You can see it. Yes. So that means the chlorine ion is larger than what its original atom. Learned a lot. Can't wait to see you next time. Thank you guys. Hope you've learned something today. Can't wait to see you next class.